So, here we go. All right. Sorry, I seem to be having trouble with my glasses and my vision this morning. And Dora is here on my lap. She's a little restless this morning. So my sound is okay, coming through. Let's get underway then. So our starting pick this morning. I've got a few left, but they're all from the same people that sent me pictures before, so I would welcome some new ones. And I know we've got students in Dhaka, Bangladesh, Turkey, China, a whole bunch of different places. So it would be Mauritius. Be appreciated to get some pictures from elsewhere. This Dominic sent me, and I think he took it from, he sent me several from, I think, at different parks that he is at. And this one is in the Tony River. I've never been there before. It's, I had to look it up between Pictou and River John along the Northumberland Strait, be looking across towards PEI. Nice quiet beach, probably early morning by the looks of it. I think that would be to the east. No, maybe not. Maybe that's sunset. I'm trying to think of what would be east-west in this one. Anyway, um, and then I had an unexpected visitor on the weekend. Like you meet my friend Bernie. We were comparing our mitts. Uh, anyway, it had my little bit of fun yesterday. It's gorgeous here down in Kingsburg. Nice crisp snow. Everything looks like a Christmas card. But having some fun here. Anyway, on we go. Yeah, I knew there had to be some way of doing it because everyone was doing it. So just Googled it and there was a video on how to do these things. So Bernie is popping up everywhere. Anyway, just a few updates. Test one. The results are incredible. I haven't really studied it other than everybody seemed to have pretty much the right answer to almost everything. The average was like 14 point something out of 16, worked out to 90%. Last term, test one, the average I think was around 70% or thereabouts. So this is a big jump. Uh, Fall term class, very different from the winter. Uh, Maybe you're at ease with being online. In the fall, there was a huge amount of stress and anxiety about being online for the first time, so that probably disrupted things. Quiz three, the scores for each of the quizzes, they've inched down a little bit. That, starting out quiz one, I think it was like 95, 96% average. Now it's about 90%. So still very, very high grades, which is very nice to see. Does seem to suggest I could probably demand a little more of you, but I am uncomfortable with multiple choice. Um, that they get to be trick questions, that type of thing. I don't want to get into that. But we do find, um, just a heads up, when we get into chapter 4, we're getting to pivot tables. I know students had a lot of trouble with my quiz questions on it, and they had a little bit of trouble into the next couple of chapters as well. It's more demanding work. It's less on memorizing jargon, that type of thing. So, but at this rate, with the quiz scores, even last fall, they were always very high. Not quite as high as where you guys are. But this bodes well for test two, which students had a lot of trouble with last time. So hopefully things will work. Assignment one is posted and already getting quite a few emails in all the sections. Seems to be the same problem that people are using Vlookup. They type it in and then they press enter, and all that happens is their formula stays there. It doesn't execute the formula. It doesn't do anything. Nothing happens. And I encountered this as well a week ago. It was the first time I've ever seen it happen to me. Was totally confused. I had to get someone to help me out. Turned out Excel, when I'd added a column, it created a column full called text. And so anything typed into it, it thought was text. So it thought the formula was text and just accepted it, didn't do anything with it. So what I had to do was go and take all the cells in that column, select them all, and change the format to general. That I'll show you once we get into Excel today, what that looks like, just to make sure you understand. That last term, at the end of the term, I did a survey of the class. What was it I could do to improve the class? And they had two strong recommendations, lots of students saying. One was that they wanted sample problems. So at that stage, we didn't have a body of old assignment questions, and even so, there were Excel questions. So it was sort of tricky. The other was they wanted more how-to videos on things that I had done at the first part of the class, but then stopped doing. So taking their advice in mind, you should find on Top Hat that there is a folder for assignment 1 from the fall. And in it, you'll find the assignment 1 questions and the marking key, the solutions key for it. Your assignment is almost the same type of tasks, but whereas they were doing it on the fall survey, you're doing it on the winter survey, and there's some other slight differences between the two. The surveys were different, and the output ended up being different, a whole bunch of little things. So that may be helpful to you. But the other is they wanted how-to. So I went back and recorded 2 videos, 20 minutes or so each. First one on questions 1 to 4, which are preparing our data, and then the questions 5 through 8, which are initial exploration of the data. And so I walked through the assignment, doing the Excel portion, and also talking about the other questions. So there is some broader commentary, but you may find it there. It's useful in terms of figuring out how to. And that tomorrow afternoon, I'll be doing a session for the Math Help Center staff on the assignment and walking them through some of those sorts of things. So they're a group that last class I gave you information about signing up with them and their different sessions, and that they should as well be able to help you through some of the Excel stuff. But otherwise, email me like students have already been doing, and I try to get back fairly quickly. Don't bang your head against the wall getting frustrated with material. I do that enough myself. You've got someone to ask, that's me. I've started finding people to ask as well when I get stuck. So it's Excel can be finicky. Yeah. So last day, we cluster data into groups, made a frequency distribution, that type of thing. And we were looking at small values, middle values, large values. Is our data spread out? Was it clustered together? That we tried to communicate that using a frequency distribution or histogram. And we were using the table row in Excel to be able to find some of these sorts of things. And we're using the histogram function in Excel. Both methods, they're fine as a starting point, but they're sort of clumsy. And we're going to go through one more clumsy class today, I find with Excel. But those are the most frequently used tools. Most people, when doing it, seem to be doing. There is a much better way to do it. And so part of it is I want you to be familiar with the practice you would see in a stats class and what others might be using. And on Wednesday and next Monday, show you pivot tables, which are one of the most powerful features of Excel. I love them. Do them for everything. So what we're going to do today is look at numeric summary, summarizing things down to single numbers, looking at the most common measures of that. Many of them you may have heard before, that these would be ones you would usually be introduced at the start of a statistics course, and trying to give you not just formulas, because you're not going to calculate this by hand. You'll use a computer to do it. So if the formula isn't important, what is? It's understanding what they are and how they can be deceptive or informative. Okay. So if I'm giving you a test back, like today, you may be wondering about your test. You got it back and you got a 15 out of 16 and you're all excited to find out that the class average was only a little bit less. Okay, you did great, but lots of other people did great. It's generally the case, though, when we get a test back, especially as it's a hard test, that the first thing we want to know is how did we do? And you can't evaluate your grade without having a sense of what the other grades look like. You need a benchmark, some type of standard for comparison. So what's a big number? What's a small number? It's like compared to what? They're relative to some standard. And so that's where we start thinking about, why do we look at the average? We're looking at some type of standard for comparison. And the most common measure of a standard is the average. Where's the middle? Who's in the middle? And average in statistics, okay, not in, there's the jargon used in technical academic area of statistics, and there's language the way we use it in talking to one another. Among statisticians, they talk of average in a very fuzzy fashion. They get down to very specific terms. They use other types of jargon like measures of central location. What do you mean? They're measures of the middle. Where is the middle? And the most common measures are the mean and the median. There are others, but nobody uses them. Mean and median, the only two you should ever use, because your audience won't understand the others. The mean is the one we usually think of as average. What we do is we take all the numbers, add them all up, divide through by the number of values we get, and we get an answer out. So as a formula, you won't need it in this class as a formula, because I won't make you do this by hand for working out average. You'd always use something like Excel to do it, or a calculator at the very least. So you add up all the observations, divide by the number of observations. In a stats class, they'll probably give you a formula and they'll start using symbols. So they use this X with a line over the top, X bar they call it, as being the sample average, sample mean. They like to use the word mean instead of average. And they use this squiggly guy here, X. That means the sum of all the values X. And N is the symbol they usually use for the number of values they've got. So X is usually what we're measuring. N is the number of observations we have. That each value is treated the same. They're all equally important, and we include all of them. You may feel some values may be more important than others, and sometimes we have a weighted mean, and we give some values more weight than another. That's beyond our scope and should only be used in particular well-intentioned situations. And sometimes we don't use all the observations. That some people like to use what we'd call a trimmed mean. They trim off the ends. They trim off the really low values and the really high values. We're going to actually do that. I like to do that. I always have trouble with the extremes. And it messes up statistical theory to do it, but there's often good reason for doing it. It helps things out. So if I went into the total row in Excel, and last time I think we did this, we found the average, like the average or the mean expected salary was 52,914. I used all the values. I think last class we also trimmed out the really small ones and the really big ones. That would be called a trim mean. And we thought it might be more reliable because of these outliers that we had there. But technically, we're supposed to include all of them if we're calculating the mean. Now, the median is another measure that's usually similar to the mean, and it's used particularly in cases where we are concerned about outliers. We don't want to talk about the people at the end. We don't care about them. We'd like to know about the middle. So one way of getting the middle, if you were all in a classroom and I wanted to know what was the typical height of students in the class, I could line you all up from the shortest person to the tallest person in the room. Just had you line up across the front. And then without doing any measurements of all you people, I could visually see shortest to tallest. Just put you in ascending order and then grab the person that's in the middle of that list. That person would be the median, is in the middle in the sense of halfway between the one end of the class and the other end of the class. So I can sort my values, smallest to largest, pick the middle value. That it's not typically in the total row, but you can get it. I used to using it because back in the dark ages, when I was first doing this type of thing, we did a lot by hand. And I can find the median quite easily by hand by sorting my data set, finding that middle section, and then just counting and finding the person in the middle. Let me look at my data set. Here was the one we had last class, I think. And so here were the salary figures. As I said before, I could, have I got a total row in here? Make sure I do. Yeah. So I could go down to the bottom here. There was my average. That is the mean. And so in Excel, it's called the average. I could find the middle, the median, by going to more functions, and there's a lot of these different ones. And some of them are grouped. I could look at statistical. Got to be in here somewhere. There it is. There's the median. And hopefully it works. There it is, 50,000. So there's the middle of the list. Or I could have done this and done a sort, say smallest to largest. So smallest is in row 2. That's the 0. It's not going to sort the blanks for me. It'll put them all at the end. Highest value here is 753. So the middle would be 377. So I could go back up here and look at, where are we? There, there. That must be around the middle. Okay. Oh, sorry. Someone asked something and I wasn't paying attention. Now it says got it. I think I'm on screen share. Oops. Somehow I just lost my presentation. Excuse me. I'll get back there. Oh, there we are. So I could sort the salary column. I counted down, sorry, it was 752. It was row 753. So I divided it by 2. I get 376. So I could count 376 from the top or 376 from the bottom. Those are 2 different values. Well, they both turn out to be 50,000. If they were different, if one was 50 and the other was 52, I would just average the 2. So if when counting up and down from each end, generally doesn't matter if you've got a big data set. So in that sense, it's in the middle. Which one do you use? Why should you use each? The median is nice because it's not affected by the extreme values. I don't have to trim anything off because I'm really ignoring the ends. I'm only looking at the values that are in the middle of the data set. So if my largest value is 650,000 or my largest value is 165,000, won't change my median, but it will change the mean because it looks at all of those precise values. So the median is nice in that it's not affected by those outliers. But when you talk of average, almost everybody thinks of that traditional sense of adding everything up, dividing by the number of values. And so you have to take time to explain what the median is to many different audiences. If you have to do that, good chance you're going to lose a bunch of people. That, oh, what did I do? Sorry. There, I got it. So as much as I might like the median, since it's standard practice or everybody thinks mentally of average being that average, it's tricky to use it. Nonetheless, if my data is highly skewed, and we had that last class, if you look at, do I have it in my Excel file? Excuse me. No, I don't. I don't think. No, I threw it away. Oh, no, it's not sitting there. Sorry. But if you remember, we had a histogram that bunched at the beginning and then a long tail to the right. When you've got a skewed distribution, the mean gets pulled by those really high values. The big numbers pull the mean over towards the big numbers, whereas the median tends to stay in the middle of that bubble that you've got there. And so if you're looking at highly skewed data, and this comes up with most financial data. If I was looking at the average house price in Halifax and looked at the average number, I might get a figure like, I don't know, $410,000. Big, it's expensive because we got a lot of really expensive homes. But if you looked at what the median house price is, 50% or smaller, 50% or larger, so you're shopping for a house that's sort of in the middle of the price range, the middle of those houses for sale might not be 410,000, it might be 340,000. That big bunch of small houses, and they're lower priced ones, and they're between 200 and 350, the ones that sell a lot of. That's where the typical first time buyer is going to be. And those $1 million homes that's dragging the mean value up are not ones we typically buy. So it's deceptive to look at mean house prices. It may be more meaningful to look at, why is this scrolling on me? Stop that. I don't know what it's doing. Oh, excuse me. Dora was snoozing on my keyboard. Okay, back, where am I now? Okay. So if you got, if it was on a test and you were told, you got 82 on a test, and you asked what the average was, and you heard it was 68. Yes, she's always trying to help. That you'd say, oh, the average was 68. I got an 82. Am I at the top of the class? So what are really high grades on that test? That, or on the other extreme, suppose the average was 62 and you got 51, and you're wondering, oh God, at least I passed. I wonder how many failed. I wonder how many did worse than me. You'd like to know what the low values are, what the high values are. But if you've got a big data set, low and high are crazy numbers. They're the extremes. They're the outliers. So maybe we want to look part way up. With incomes, if you're talking about high income people, There's often in the media we hear about the top 1%. Top 1% seem to earn 20 or 30% of all wages paid, a disproportionate number of the income among that top 1%. And so if you're looking at what are super high salaries, let's not look at the highest paid person, but what does it take to get into the top 1%? Or if you want to scale it back, what does it take to get into the top 10%? What grade would you need on a test to get into the top 10% of the class? So these things, we'll see in a minute, are called percentiles. So I've got 752 students that gave me a salary figure. 1% would be 7.5. So that would be the eighth from the top. So if I sorted them largest to smallest, I could find, go do that. Where am I here? So let me sort these, largest to smallest, go up to the top, and I'd just count down 1, 2, 3, 4, 5, 6, 7, 8, 175,000. That would be that top 1%. If you're above 175,000, you're in the top 1%. That what about being in the top 10%? Well, that would be what, 75. So I could count down 75 from the top. It's one way. Yeah, it's a long way to count. That would be, now my first row is the header. So let's go down to number 76. There it is. Oops. $80,000. So if you expected to earn more than 80,000, you'd be in the top 10%. The other way is looking from the other end. How far would you have to count? If 10% are up here, 90% are down there. 10 plus 90 is 100. So very often we end up talking about counting from smallest to largest as opposed to largest to smallest. Oops, let's move over here. That since 90% are below 80,000, we call it the 90th percentile. If 99% are below 175,000, we'd call it the 99th percentile. So these, like the median, are nice because they're not really influenced by outliers. We don't look at the most extreme values. We count a ways back from that. And so except for, maybe looking at the 99th percentile or the 1 or 2nd percentile, the ones at the extreme, we shouldn't be influenced a lot by outliers. And many people use these to define high and low. So is high the 99th percentile? Is it the 90th percentile? Is it the 75th percentile? Different people will define high different ways. There's no accepted standard there. So there's some other approaches. Some people like to use quartiles. Take my data, slice it in half. So I've sliced it at 50,000. Half of them are below 50,000, half are above 50,000. Now take the first half and cut it in half, make quarters. And I'd have, it's like splitting things up to 25%, then 25, then 25, then 25. So I've split it into 4 comparable groups. And from there, I can work out what's the first quartile, second quartile, which is the median. Second quartile, I've got the first 25, the next 25. So that's in total 50. So that would be the median. And then the next 25, and then the rest are above that. And some people might look at the first quartile as being low, third quartile as being high. That economists, and I've done it when looking at groups, if I wanted to see what's the difference, if I was creating profiles of students having academic difficulty versus profiles of students having academic success. What I might do is identify all those students in the first quartile, the bottom 25%, and then look at all those students in the fourth quartile, the ones that in the top 25%. And for each of those groups, I'd build a profile about where they're from, what their gender is, what their age is, how they did in high school, what major they've got, what program they're in, how they did in certain courses. And from there, I could get a sense of what does a successful student look like? What does an unsuccessful student look like? And how then can I move the unsuccessful ones? Are there some characteristics that I have the ability to change or give extra support to move them from one group to the other? And so I like quartiles for identifying my extreme groups and see how they compare. Um, if you're in marketing, you'd look at your top 25% of customers and your worst 25% of customers and see what's the difference and how do I take someone from the first quartile and move them up to that fourth quartile. So they're very useful in identifying the low group and the high group. And they're simple. They're really easy to find. Another thing that we'd like to talk about the data set that we're already getting a sense of from high and low is diversity in the data set. Are all the people in the data set doing about the same, or are they very different from one another? With your test, the average is so high that it's really a very homogeneous bunch, that the difference between a student that got 14, 15, 16 out of 16 is nothing. The if I reset the test or ask slightly different questions, someone that got 16 the first time might well get 14 or 15 the next time, and someone that had 14 the first time might get 16 the next time. Those differences are negligible. So, except for a few students that had trouble with the test, for the most part, it's a very homogeneous group. If my purpose was to identify the difference or separate you between those that have super understanding of material versus those that just have an adequate one, doesn't do it. I'm not getting a lot of diversity in the results. I'm not worried about that. I'm not trying to do grading in the sense of who's grade A, grade B, and that type of thing. At the moment, I want to see you understand it, have a basic understanding or not. And at the moment, everybody seems to. Great. That But there are many instances where we do want diversity or we'd like to measure that diversity. And how do I measure it? Simplest measure, I could take the maximum minus minimum and look at the gap there and see, is it a big gap between the best and the worst or a small gap? Maybe I look at the gap between uh, the first quartile and the third quartile and see what the spread is there between my high value and low value. Maybe it's between the 10th percentile and the 90th percentile. I could come up with all kinds of measures like that. But most folks don't use those sorts of measures. They like to calculate diversity in a more complicated fashion. We'll go back later and look at calculating it in the most simple fashion, or one of the most simple fashions, that when doing some actually graphical work later. But for now, most measures look at deviations from the mean. And this may seem straightforward, but the language may get you hung up. So here's what I mean. So the mean is 52,915. So if a student said they expected to earn 20, they're $32,000 below the mean. I get a negative here if I take the difference. If someone said they expected to earn 65,000, oh, they're $12,000 above the mean. It's a positive number. So I could look at those differences. Are those differences small or are they large? On average, are they small or large? That um, and so one measure is called the mean absolute deviation. That you take all of those differences that you calculate, ignore the minus signs because I don't care about the minus 32 versus a plus 32. It's still $32,000 away, and average them out. The MAD is something that uh, statisticians never really liked because it has awful theory. Excuse me, my headset is tied up around. What are you doing to me here? You're strangling yourself. There we go. Um, it's not. It has very bad theoretical properties, and statisticians don't like it. But years ago, practitioners loved it because they could calculate it by hand, again, or on a basic manual calculator in the old days. And it was heavily used in forecasting. They talked about, on average, how far off is my forecast? And so this, and we still see it today. Some people in forecasting will use this measure, but we won't. Um, uh, it's intuitively appealing, but it generally isn't widely used. Mathematicians like to get rid of negative signs, and we'll see this again later, by squaring numbers. So instead of taking -4 and just removing the minus sign, they say, oh no, take -4, square it, and I get +16. So I get rid of the negative signs by squaring instead of absolute values. Absolute values um, make bad theory because behind the scenes they end up using calculus, and calculus doesn't like absolute values. So we're not doing that stuff. So they calculate a thing that has to do with the average squared difference. So I mentioned before, x is the different values we've got. X bar, the one with the line on top, is the middle. So I'd take my 20,000 minus 52,000. I take the difference, I square it. I do that with every number, add them all up. Why do we divide by n minus 1? Not, we had 752 values. I'm going to divide by 751. Why? Nicer theory. This is all driven by the theory gets better. And there are arguments about biasing things that are beyond the scope of what we're doing here. To be honest, with big samples, it doesn't make any difference. And they call this term the variance. That, and you will see the term variance coming up in a statistics course in different contexts. Finance people also look at variance. They look at it in the variability of stock market returns, and they like to measure variance. But think of the units you're using. No, you will never be required to use a formula. Okay. That I think it's insane for you to make you calculate things by hand when we've got tools to do it. Some instructors still feel strongly about that, but they don't do things like square roots. When I was a student, I was taught how to find a square root, how to do long division, those sorts of things. You don't see people doing that anymore by hand. They use a calculator. Well, if you'll use a calculator or a computer to do those things, why not use it for everything else in terms of arithmetic? There's nothing you're going to learn by doing it by hand. But do understand that from the formula, what's happening here. This is taking every value, seeing how far you are above and below the middle, squaring those differences, adding them all up, averaging them out. I always like to look at the units of my measurement. So if these were dollars, well, because I squared them, they become square dollars. With this data set we had on salaries, I end up with 1,940,900,000,000, oh, sorry, no, 1,940,893,817.64 square dollars. awfully big number, and the dollars are square dollars. What does a square dollar look like? Don't carry them in my pocket. My bank card doesn't let me withdraw square dollars from a bank machine. So the easy way to fix that is take a square root, and then it takes square dollars and makes them into real dollars. Fine. So I've got $44,000. So let me think. You're telling me, look at each of the values, look how far they are from the middle, square those numbers, average them out, sort of, because you're going to divide by n minus 1, and then take a square root. Okay? It's called the standard deviation. That's the name that's used for it. And it is far and away the most widely used measure of variability. If you'd like to have an intuitive understanding of a formula, don't. Uh, they've taken the numbers, put them in a food processor, blended it all up, and they poured out their smoothie. Okay, smoothie doesn't look anything like what it started with. It doesn't look like the berries and the yogurt and everything else that you put into the blender. It's this goopy thing in a glass. That's what standard deviation is. Don't overthink it. Okay? It's a measure of variability. And I'm not sure knowing where it came from helps you at all. So knowing the formula, does it matter? But it does turn out, and this is something we're going to use a lot in different contexts, we're going to use a rule called the empirical rule. And if our data situation is roughly bell-shaped, okay, that it doesn't have a lot of outliers in it, okay, it doesn't look heavily skewed. Remember a bell curve, shaped like a bell. It's skewed if someone hits it, and so it's a bit of a bump with a long tail, or a long tail and then a bump at the end. That as long as it's sort of balanced on the two sides, this rule generally works fairly well. And it's a way of using standard deviation to get new insights. We're going to use it a lot. And hopefully the later cases we'll use it in, we are going to get this bell shape. You may also hear it referred to as a normal distribution. Don't worry about the jargon. In stats, you're going to hear this over and over again. This empirical rule is something you should always remember. Carry it around with you like, a basic tool you'd use. If it's reasonably symmetrical, you take your mean and take one standard deviation below, one standard deviation above, you have about 2/3 of your data. 2/3 of the time, 68% of the time, you should be in that range. If you step out 2 standard deviations below and 2 standard deviations above, you should have about 95% of your data. And it should be unusual. It does happen, but it's unusual to be more than 3 standard deviations away. Now, this data, we've got outliers, and it is skewed. So this is not going to work, but we'll do it twice. So if I went out 1 standard deviation, my standard deviation is quite big. It's 44,000. It means below, I'm going to be at around $9,000 and above around $97,000. I looked at my data, I'm going to find much more than 2/3 of students said they expected to earn between $9,000 and $97,000. And if I went out 2 standard deviations, I'd get silly numbers. I'm going to end up with something like minus $35,000 and plus 100 and about 140,000. They're a huge range. These numbers are messed up because I've got outliers. My data is skewed. But if I was to trim off the extreme values, say one's below 10,000 and above 120, let me just go back to Excel here. If I go down to the bottom here, my total row, and I ask, give me, my total row, It has standard deviation. That's where I got my 44 from. But if I did a filter here and said, give me between 10, oops, and 120, let's take out the outliers there. I get $20,000 as my standard deviation. It's much, much smaller. This is a huge drop. And then if I go and look out either way, that, oh, by the way, the mean changes. The mean gets to be around 50. So it's going to say 2/3 of the values are between 50 minus 20 and 50 plus 20. So that's $30,000 to $70,000. You're going to find about 2/3 of them are in that range. And most of them are between 90,000 or 10,000 and 90,000. And that you're going to find fits with your data reasonably well. It, as long as we don't have the outliers, it tends to work. Why do I do it? Before, I wanted to define what's a low value and a high value. I've talked about percentiles and other sorts of things. If I know the mean is 50 and the standard deviation is 20, I can say that very low is 10,000, low is 30, middle is 50, high is 70, very high is 90. If you're beyond 90, you're extremely high in terms of the values. I can summarize my whole data set with 5 numbers that are defining from very low up to very high, somewhere in between, and what's the middle. So the standard deviation is a tool I use to use empirical rule to get these things. I still mentally can understand middle, the 50,000. That standard deviation is a way of me identifying what's low and what's high from the middle. And if my data is reasonably symmetrical, it worked quite well. So it's useful because sometimes we want quick and dirty little tools to appreciate our data, and we'll use it a lot in the future. Now, you can calculate, we've been using the total row. There's another way of getting a bunch of summary measures, and they are in that data analysis toolkit. So I'm going to go and get that. So where am I here? Excel. I'm going to go up here to data analysis. Okay. And what we've been doing are called descriptive statistics. They describe the data. Statistics classically as measures were just measures, like baseball statistics, runs batted in, batting average, a whole bunch of statistics on players or on teams. That's where this came from, as being very descriptive statistics, is that sort of thing. That's where the language came from, or the words. If I click on this, it gives me a thing that says, okay, where is the data? Well, my data, excuse me, I better, not going to like this. I'm going to go and select, excuse me, I better go backwards here. I want to take my filter off here. Okay, now I'm going to go to data, data analysis, descriptive statistics. My data is in this column here. Okay. Salary column. I can go and highlight all the data if I like, or I can just tell it the references. It's in column L. I'm going to go from the first row all the way to, I can go to 812. I'll include the blanks and see what it does. Okay. I've got labels in my first row. I'm going to put it in a new sheet. Generally with these things, I always put them in a new sheet so that I don't clutter up my data set. And I want summary statistics. It's rare that I ever want to play with the rest of these things. Summary statistics is the only one you really need to know. And I click OK. Okay, let me make this bigger. and make the columns wider so you can read it. So it says up here that the mean is 52,914. We already found that. The median is 50. We already did that guy. Okay. That make these wider. We can, oops. Okay. These two here, and I'm going to highlight the only ones you should pay attention to. Okay. These ones are useful to us. I told you about the variance before. This is where the 1,940,000,000 figure comes from. So that you may want to find. Standard deviation, we did. That's our measure of variability. We've looked at the minimum, that was 0, and the maximum. These are things we took out of the total row. Okay? We've looked at how many values did we work with. There were only 752. Although I had 812 rows, only 752 numbers I'm working with. Okay. So what about the rest? Well, the sum is just adding all the numbers together. Okay. I don't know what I'd use it for. The range, that's the difference between the maximum and the minimum. You might want that one. Okay. Other ones, what's the mode? The mode is the value that occurs most frequently. Okay. Now, since I was asking students, or in the survey, we asked them to self-report, they rounded off the numbers. Suppose this was a survey of students' actual earnings 2 years after graduation, and I got data from the Canada Revenue Agency, CRA, the tax people. So I know exactly what their income was, right down to the penny. And maybe I've got 752 different numbers, and they're probably different from each other by small amounts, maybe, but they're probably 752 different numbers. A few might be the same. The mode is the value that occurs most frequently. So if I had 2 or 3 people reporting the same income, then that could well be my mode, but it only represents 2 or 3 people, not anything important. Mode is something, don't use it, don't report it. If I had, can't really draw you a picture here, but if you could imagine a histogram that went up and then came down again, where is the peak of this? Where is the highest point? That, in a sense, is what the mode is supposed to represent. So if you've got a curve, it suggests where is the top of the curve, which may be interesting. But generally with sample data, it's a meaningless number. Don't use it, please. It's just going to be clutter. You'll have to explain it to people and everything. If you got to explain it, they're not going to use it. Kurtosis. I can't even remember how it's calculated, and I can't even remember how to interpret the number. What I can say is, if I've got a bell-shaped curve, okay, it goes up, it goes down again. Down at the bottom, does it just taper right down flat, or does it go out with big, is it a thin crust pizza or a thick crust one? Does it look like the tails are really fat going out, or are they really skinny? And when it comes up, does it come up nicely rounded, or does it come up just like a column that's really tight? So imagine me being really tight in the middle with big fat tails at the end. That would be a case where we've got a lot of kurtosis. Do you care? Most of the time we don't. Don't worry about it. Skewness is talked before about, you could have a skew where you've got a big bulge and then a long tail off to the side, or you've got a long tail and then a bulge. Okay, both of those are skewed different ways. Skewness is a number, could be negative, could be positive, that tells you, does it look like it's been pushed to the left or to the right or is it just sort of symmetrical? Do I need a number? Picture conveys that a lot better. I've never in all my years used either of those two things, and it's very rare to. So ignore them. They're not important to you. Skewness as a concept, yes. Um, Kurtosis, it does arise in certain applications, but ones that you aren't going to want to worry about. So it only leaves me one, standard error. Okay, this one is important. I'm going to bring this up throughout the rest of the course. It takes a long time to understand it. It's an important concept in statistics, and I don't think most students in a stats course ever understand it. It would be nice if at the end of this course you had a general understanding of what it is. It's like a standard deviation, but different. And I think I explained it in my slides. Okay. So we did all those. Mode, most frequently occurring value. Kurtosis, fat tails. Skewness, is it left or right tail? Don't pay attention. But the standard error. This one, you're not going to grasp right away. Or if you do, it's great. If you do, it's amazing if you do. But it is important. The mean that we've got, the 52,912, is only an estimate. It's based upon 752 students that gave me a number in the survey. If you could imagine me doing the survey again, and I randomly select a bunch of people and they participate in the survey, they're going to report different numbers because I've grabbed a different group. If I went out and grabbed another group, I'm going to get a different mean value. Each group I grab, I'm not purposely picking groups, saying, a low group and a high group. I'm just randomly picking 752 students. Each time I grab them, they're slightly different people. So I'm going to get slightly different numbers. They won't all, the mean values, I would hope, would be similar. Because if I'm trying to generalize and say that the average salary that students expect to earn is 52,916, I'd like to have some confidence that, okay, it's not exact. I'd like to maybe say it's between 52 and 54 or 50 and $56,000, something like that, in that neighborhood, because as I go out and pick different samples, I'll get different numbers. How similar should those numbers be to 52,916? I don't know, because the only ones I've seen are the 752 I looked at. How can I talk about all the other people out there that I didn't collect data on? This is an important thing within statistics that we can prove, that we can use this standard error to help us generalize. The standard error I can calculate just based upon my sample, but it actually reflects that broader population I drew from. And just like before, I said, say the mean value is 50 and a standard deviation of 20. So I'd expect if I randomly go out and grab someone that participated in the survey, except for the outliers, I should expect 2/3 of the time to get a value between 30,000 and 70,000. I'd went one standard deviation below, one standard deviation above. So most of the time I should be within one standard deviation. And almost all the time I should be within two. So almost everybody that I looked at should have earnings between 10,000 and 90,000. So that empirical rule talked about individuals. If I know the standard error, I can talk about averages and talk about if I took different samples, I should expect that if I took another sample 2/3 of the time, don't be surprised if you get a value that's one standard error below or one standard error above. So my mean value was 53,000. So if I took another sample, I should get an answer between 51,400 and 54,600. 2/3 of the time, I might think I'm going to get something in that range. And 95% of the time, I might expect to be within 3,200. So roughly between 50,000 and 56,000. So if I said that I expect that the average earnings of graduates to be 53,000 and someone says, yeah, should I believe you? How accurate is that number? I might say, okay, it's not perfect. It's only an estimate. It could probably be as low as 50,000 or as high as 56,000. But I don't think it's really any lower than 50 or any higher than 56. It's possible, you know, but I'm sure I'm reasonably confident that if you were to go out and collect a big sample like I did, you're going to get an estimate that's somewhere between $50,000 and $56,000. So I think my number is reasonably accurate. It's accurate to within about $3,000 either way. You're going to get more into that in a statistics course like Management Science 2207. But that's all the magic that there is in what they do. They give you a whole pile of formulas for different cases, but it all comes down to the same thing. If you're estimating something and you know the standard error of your estimate, then if you were asked how accurate is the estimate, you could say it could be off by one or maybe two standard errors, but otherwise, I think it's fairly precise. And all I know is just the 752 in my sample. I really don't know anything about all the other people that didn't participate in the surveys. It's incredible that we can make that leap, but we can prove that we can make that leap. So zip through. What did we do today? All I did was focus on coming up with simple, basic measures to describe your data set. Where is the middle? What are low values? What are high values? Different ways people like to measure the middle. Different ways you might want to measure what's low and what's high. You've got to come up with some definition of when you're defining low and high. Percentiles might be one way of doing it. The other way is using that empirical rule to do it and use standard deviation and go one or two standard deviations above or below as a way of identifying high and low. And if you are asked about your estimate of the mean, it's the only estimate that we generally talk about precision to. But if someone wants to know your mean value you said was 53,000, should I believe you? Well, if I know the standard error, I can say, well, it's not exact, it's an estimate. But I don't think the estimate is going to be off by more than one or two standard errors. And I know what that is, $1,600. And that is, we're frequently going to be challenged on the accuracy of our numbers. And standard error is that important concept for being able to measure that sort of thing. And it's like a standard deviation. It's a standard deviation of average values, of mean values from samples, which that may be hard to understand. But hopefully it'll come to you in time. So what we've done in the last two classes is what I'd call classical descriptive statistics. And we've done it in the classical fashion that you will find in a statistics course. If they used Excel, maybe they use some other software like Minitab or SPSS, but those are the types of things that'd be coming up out of that. And they're clumsy tools. Well, in Excel, it's very clumsy because when I'm doing the descriptive stats, just like when I did histograms, I can't do filtering. I can't look, if I want to look at the mean value for business students versus art students, I'd have to filter the data, copy it into a new sheet, do the descriptive stats for arts, then filter it for business, copy that data into another sheet, do the descriptive stats for business, do the same thing for science. Very clumsy process for doing it. But Excel has a really nice tool that's especially powerful for looking at relationships. And what I was just talking about is a relationship. How do earnings depend upon what program you're in? How do earnings depend upon when you started your program, what year of study you're in, how old you are, whatever. If you're looking for those types of things, a pivot table is a very nice little trick for doing it. And it turns out for those of us that are very visually minded, it's like before we did histograms to interpret frequency distributions. With a pivot table, we can also do a chart at the same time. And I can change the table, it'll change the chart. If I change the chart, it'll change the table. I can do flip back and forth. Very powerful combination of things. And they're really good for developing, especially the charts, to then turn around and use in presentations for other audiences. So the next two classes are going to be about using pivot tables and the associated charts. One class, we're going to focus primarily on averages and looking at messing around, and we'll get a good sense of how to manipulate our pivot table. But then we're going to look at frequency data. So just looking at gender versus where people live. So I'm not looking at an average. I'm not looking at numerical outputs. I'm looking at what we call categorical data, at nominal or ordinal data. How do we summarize that in a table and in a chart and in a fashion that we can make interpretations? Behind the scenes, we're actually going to be playing with probabilities, but I won't say that explicitly at this stage. We're going to leave that till later in the course when we look at probability in a formal fashion. So as we work through, there's behind the scenes a lot of additional layers to this. Um, right now, I'm focusing much more on mechanics of how to find numbers, how to build tables and manipulate them, and look at some deeper things on interpretation we'll leave later. It's just too much to process at once. And it gets boring looking at the same topic for too long. Anyway, we're done for today. I didn't run overtime. On Wednesday, I'll try to address issues to do with the assignment. In the interim, please, if you haven't already, start in on that assignment. Oh, I was going to show you that problem students were running into. Let me go and look at my data here. So suppose I wanted to recode things like I did in class, where I picked uh, a, in this case, I recoded home, I think, in class. Okay, let me just make my columns wider here. So I'm working on this column here, and I used a formula. I put in E equals V look up, and I had a process I went through. Or here with Nova Scotia, whoops, when I did the same thing. Okay, I did a lookup, grabbed a value, went through all of that. Notice up here, the top of my screen, I'm in the Home tab where it gives me basic things on format, what font I'm using, colors, bolding. Over here, it says General under this group called Number. Now, I could make this into dollars or percentages or format things with decimals if it was a number. It's not. Right now, it's just general. Okay, and my formula, when I put it in, worked. Suppose this thing was not general, but text. Okay, did we even pay attention to this? No, we didn't. Normally, I don't even look at this. Generally, my columns are all general unless I go in and change them. Excel has gone and done this, and every time I fix it, it seems to reset it, or it seems to randomly do it. What happens when I type in Vlookup equals Vlookup? Hey, it's got the formula, like it's making sense. I'm going to put G2. I'm going to go to my lookup table, and here was my table for home. And I'm going to put dollar signs around this. Good. New value is in column 2. And I want an exact match. So I click on false. Okay. Bracket. Didn't work. Look what's here. Let me wrap it so you can see the whole thing. It's written it all out, but it's not executed it because it thinks it's text. Okay. Now, see if I change it to general, will it fix it right away? No, it's still not working right. Okay. Take this guy out. Make sure that column is all general. And if it's general, and I go down here to my, and I'd never had this happen to me. You know, I've been doing this for years. It's never ever happened to me. Whoops, excuse me. I think this was something I would have known, but now it works. Oh, oh, I made a typo. I grabbed something incorrectly with my table. Yeah, my pivot table, I've got the wrong reference in here, I think. Okay. And it's easy to make these mistakes here. Let me go back here to lookup tables. Oh, it's still not working properly for me. Okay, I don't know what it is, but it's a separate issue from the one I wanted to show you. So if when doing your assignment and you do VLOOKUP and it just freezing, go look up at this square here and see, does it say text? And turned out for me, it was doing it to me, and it was text that was there. And I've had a couple of students email me and the other instructors as well, and it seems to be happening with them. I had one student, it worked. When you first time she used VLOOKUP, it worked. The second place she used VLOOKUP, it didn't. And that ended up being what was happening. I don't know why. Anyway, now we're pretty much out of time. So send me your questions. Also, if in the interim, uh, since your assignment looks a lot like the one from last term, look at the assignment one on top hat and look at the solutions or look at the videos and see if that gives you assistance in doing that. And we'll take up your other questions on Wednesday. Take care. Enjoy the snow while it's nice and white out there. Bye now.